The inverse of a function. In this video, we'll discover which functions are invertible, find the inverse of some familiar functions, compose a function with its inverse, and limit the domain of a function to allow an inverse. A relation is a function if there's one output, exactly one, for each input. So the domain is the input, and since each element of the domain has exactly one arrow pointing to its output in both f and g, f and g are both functions. Now sometimes we'd like to reverse a function. That is, if we know the output, we'd like to find out what input gave us that. That's called the inverse of the function. If I want to find f inverse, which is written like this, I would take the range and make it the new domain. I want the same matches, so 3 has to match to -1, 5 to 0, and 7 to 1, and I still have exactly one arrow from each element of the domain into an element of the range. On the other hand, if I try to reverse G and find G inverse, I would match 3 to -1, but I would also match 3 to 1 because I'm preserving the matches that were originally there in C. And 5 would match to 0. So the element 3 of the domain has 2 arrows to elements in the range, and so G inverse is not a function. A vertical line test can tell us whether a graph is the graph of a function or not. If each x has exactly one y, a vertical line will never pass through the graph of a function more than once. So this green graph is a function, yes, a function, but the yellow graph isn't because the same x corresponds to several different y's, and that makes it not a function. Now because the inverse switches the x's with the y's, if a horizontal line passes through a graph more than once, the graph is not invertible. Now both these graphs are functions. They both pass the vertical line test. Any x corresponds to exactly one y, but they're not both invertible. The green function is invertible because a horizontal line, any y value, goes back to exactly one x. But the yellow graph is not invertible because a horizontal line shows that y corresponds to 2 different x's. Well, if I know a function is invertible, how can I find the inverse? Here's a linear function, f of x equals 3x minus 2. Linear functions are always invertible unless they're the constant function, the graph of a horizontal line. So I know it's invertible, and if I write it with y equals 3x minus 2, and I remember that the inverse takes the y as the x and the x as the y, all I need to do is exchange. Write x where y is and write y where x is. So the blue is the original line and the red is the inverted line, but it's in the wrong form. It's not solved for y. So I'm going to solve for y. I'm going to add 2 to each side. That gives me x plus 2 equals 3y, and then I'll divide by 3 and have y equal x plus 2 divided by 3, or we could also write y equals x over 3 plus 2 over 3. That is f inverse. and it's written in terms of x, so we have f inverse of x is x over 3 plus 2/3. Now what do those two graphs look like? The original function, the blue graph, has y-intercept -2 and slope 3, so it looks like this blue line right here. And the inverse graph has slope 1/3 and y-intercept 2/3, so it goes through 2/3, and then for every 3 that it goes over, it goes up 1. So something like this red line here. Now how are those two graphs related? Well, remember, y has become x and x has become y. So what's happened is that they are reflected, the blue graph reflected through the line y equal x here is the same as the red graph, and the red graph reflected through the line y equal x is the blue graph. If you think about the action of a function with its inverse, the original function takes us from x to y, but the inverse takes us back from y to the original x. Well, that means that if I compose a function with its inverse, I should get back to the original x. So let's try it. F of f inverse means take f and put f inverse where x should be, so I write in f inverse there, and then I simplify. The 3 outside the parentheses cancels with the denominator, so I have x plus 2 minus 2, which is just x. F inverse says to take x, add 2, and divide by 3, so if I substitute what f is, it's 3x minus 2, and then I simplify, I find that it's 3x minus 2 plus 2 divided by 3, or 3x over 3, which is just x. A function composed with its inverse takes us back to the original x. Here's the graph of y equal x squared, and although it's a function, it's not invertible because it doesn't pass the horizontal line test. But it's important for a function to be invertible. We often want to go backwards, and so what we do is force this function to be invertible by limiting the domain. So if I limit my domain to x greater than or equal to 0, to find the inverse, I exchange x and y, so now y squared equals x, and solve for y by taking the square root of each side. Now that only works if y is positive and x is positive, so y equals the square root of x is f inverse, but only for the right-hand side of the branch, because this result is always positive. The graph of the square root is the reflection of the graph of x squared through the line y equal x, so it acts just like an inverse, but it's only for the positive branch. This video covered quite a bit, so here's a summary. By definition, a function has exactly one output for each input. But if it also has exactly one input for each output, it's called one-to-one, or invertible. The inverse function reverses the relation of the original function, taking the output of the original as the input of the inverse. And the inverse is notated f with a little -1 exponent. If a function is composed with its inverse, the result is the original input. The horizontal line test says that if a horizontal line passes through the graph of a function more than once, the function's not invertible. Linear functions, except for horizontal lines, are invertible. And we sometimes restrict the domain of a function so that it will have an inverse. To find the inverse of a function given as a graph, reflect the graph through the line y equal x. And to find the inverse of a function given by an equation, exchange the variables x and y and solve for y.